Max Planck's discovery of energy quantization stands as one of the most pivotal moments in the history of science. It is an achievement that not only marked the birth of quantum theory but also initiated a seismic shift in the understanding of the universe. The impact of Planck's work reverberated through the scientific community, challenging centuries-old assumptions about the nature of energy, matter, and the laws governing the physical world. His discovery, while initially controversial and difficult to accept, ultimately laid the foundation for modern physics and transformed the scientific landscape forever. To understand the magnitude of Planck's discovery, it is essential to recognize the context in which it occurred. Before Planck, classical physics, governed largely by the laws of Newtonian mechanics and the wave theory of light, held a firm grip on scientific thought. Energy, according to classical theory, was viewed as a continuous entity, flowing in a smooth, uninterrupted manner. The concept of energy quanta, on the other hand, was almost unfathomable in this framework. The idea that energy could exist in discrete, indivisible packets would challenge the very core of classical physics. The problem that led Planck to his groundbreaking insight was related to blackbody radiation. A blackbody is a theoretical object that absorbs all incident electromagnetic radiation and re-emits it, acting as a perfect radiator. Scientists had been grappling with the question of how to explain the radiation emitted by such a body across different wavelengths of light. In the late 19th century, the laws of radiation were well understood in many respects, but there was a glaring discrepancy. Classical theories predicted that as the temperature of a blackbody increased, its radiation intensity would grow without bound, especially at shorter wavelengths, leading to what became known as the ultraviolet catastrophe. In simple terms, classical physics suggested that blackbodies would emit infinite amounts of energy at short wavelengths, a conclusion that was physically absurd and contradicted experimental observations. This conundrum was a profound problem in physics, and it was widely accepted that a solution was needed. The classical theories had failed to explain the behavior of radiation, and a new approach was required. Planck, at the time, was working on the issue of radiation as part of his duties at the University of Berlin. He was deeply aware of the failure of classical physics to account for the experimental data, and this awareness led him to seek a new way forward. He approached the problem by considering the nature of energy itself, and it was in this moment of insight that Planck made a revolutionary realization. Planck proposed that energy, rather than being emitted or absorbed in a continuous fashion, is actually quantized. He suggested that energy could only be transferred in specific, discrete amounts, which he called quanta. This was a radical departure from the prevailing view of energy, which was assumed to be infinitely divisible. The energy of a system, according to Planck's hypothesis, was proportional to the frequency of the radiation being emitted or absorbed, with a constant factor, now known as Planck's constant, denoted by the symbol He. This constant became one of the most important numbers in all of physics. Planck's work provided a mathematical formulation that could accurately describe the spectrum of blackbody radiation. His equation, known as the Planck distribution, explained the observed intensity of radiation across different wavelengths. For the first time, the ultraviolet catastrophe was avoided, and the experimental data could be explained by a theoretical model. Planck's approach was not merely a mathematical trick, it marked a profound shift in the understanding of how energy operates on a fundamental level. The introduction of the concept of quanta by Planck was groundbreaking, but it was met with significant resistance. Many scientists, particularly those loyal to classical physics, found it difficult to accept the notion that energy was not continuous, but rather existed in discrete packets. The idea of energy quanta seemed to defy intuition and was at odds with the smooth, continuous nature of physical processes that had been so central to classical mechanics. However, despite initial skepticism, Planck's ideas began to gain traction. His work laid the groundwork for further developments in quantum mechanics, which would be advanced by other great minds such as Albert Einstein, Niels Bohr, and Werner Heisenberg. In fact, it was Einstein's explanation of the photoelectric effect in 1905, building on Planck's work, that helped solidify the quantum theory. Einstein showed that light itself was quantized, behaving as both a wave and a particle, a concept that was revolutionary in its own right. The dual nature of light would later become one of the central features of quantum mechanics, and it all stemmed from Planck's initial insight into the quantization of energy. As more scientists embraced Planck's ideas, the implications of his work began to unfold. The development of quantum mechanics, as it is understood today, owes its very existence to Planck's discovery. The theory not only altered the way physicists thought about energy and matter, but it also provided the theoretical foundation for technologies that have shaped the modern world. Semiconductors, lasers, and even modern computers are all products of the quantum revolution that Planck initiated. Without Planck's work, many of the technological advancements of the 20th and 21st centuries would not have been possible. Planck's revolution did not stop with his discovery of energy quantization. His work opened the door to a deeper understanding of the behavior of particles at the atomic and subatomic levels. For example, Planck's constant, Ha, became a fundamental constant in the equations that govern quantum mechanics. This constant is a measure of the smallest possible unit of action, a concept that is crucial in the understanding of quantum phenomena. The introduction of quantization allowed scientists to explain phenomena that had previously been mysterious, such as the behavior of electrons in atoms, the structure of atomic spectra, and the wave-particle duality of light. The consequences of Planck's discovery were far-reaching, and they were not limited to physics alone. His ideas permeated other areas of science and philosophy, challenging the very nature of reality itself. The concept that energy is quantized rather than continuous suggested that the universe is fundamentally different from what we had once believed. Planck's work sparked a philosophical revolution that raised questions about determinism, causality, and the nature of the physical world. It led to the realization that the universe is not a smooth, predictable machine, but rather a probabilistic system where events occur with a certain degree of uncertainty. The influence of Planck's work also extended beyond the realm of science. The quantum revolution had profound effects on the development of technology, the growth of industries, and the very way we live our lives. The discoveries that followed in the wake of Planck's ideas have shaped the modern world in ways that were unimaginable at the time. Today, we live in a world dominated by quantum technologies. From the computers we use to the telecommunications systems that connect us globally, Planck's work laid the groundwork for all of this. In conclusion, Max Planck's discovery of energy quantization was nothing short of revolutionary. It altered the course of physics, sparked a philosophical upheaval, and paved the way for the technological advancements that define the modern world. His ideas were initially met with skepticism, but over time they gained acceptance, and the quantum theory became one of the most successful and profound scientific theories ever developed. Planck's work is a testament to the power of insight, perseverance, and the willingness to challenge established ideas. His discovery will continue to shape the future of science and technology for generations to come. Max Planck's groundbreaking discovery in 1900, which introduced the idea of quantized energy, is often regarded as the starting point of quantum theory and a pivotal moment in the evolution of modern physics. It wasn't just a small adjustment to existing theories, it was a paradigm shift. Planck's revolution fundamentally altered the way we understood the universe, particularly the behavior of energy and matter at microscopic scales. His work brought forth an entirely new realm of possibilities for science, and his ideas have continued to influence physics, technology, and even philosophy in ways that were not initially foreseen. The impact of Planck's quantization of energy cannot be overstated. Before Planck, classical physics, which was largely based on Newtonian mechanics, viewed the universe as a predictable, deterministic system. Energy, under classical theories, was considered to be a continuous entity, capable of being transferred and transformed in any amount. This understanding worked well for many practical applications in the macroscopic world, but it failed when applied to atomic and subatomic phenomena, particularly in the case of blackbody radiation. Planck's hypothesis that energy exists in discrete packets was not just a solution to this particular problem, but a doorway to a completely new way of thinking about the fundamental workings of nature. At the time, the blackbody radiation problem was one of the most pressing issues in physics. Scientists could not reconcile the experimental data with the predictions made by classical physics. The classical theories, especially the Rayleigh-Jeans law, suggested that as the temperature of an object increased, it would emit an ever-increasing amount of radiation at shorter wavelengths, eventually leading to infinite energy, which was clearly nonsensical. This issue came to be known as the ultraviolet catastrophe. The experimental observations, however, showed a much different picture. The radiation intensity of blackbodies decreased at higher frequencies, contrary to what the classical laws predicted. Planck's approach was both innovative and counterintuitive. He hypothesized that energy could not be emitted or absorbed in a continuous fashion, as classical physics had assumed, but rather in discrete chunks, or quanta. The energy of each quantum was proportional to the frequency of the radiation, and Planck introduced a constant now famously known as Planck's constant, symbolized by He, which helped to define the size of these quanta. This constant became a fundamental feature of quantum mechanics and remains one of the most important numbers in all of physics. Planck's resolution to the blackbody radiation problem was revolutionary because it was the first step in moving beyond the classical understanding of physics. His theory not only avoided the ultraviolet catastrophe, but also provided a way to describe the observed spectrum of radiation. His formulation explained the experimental data perfectly, and for the first time, there was a mathematical framework that accurately predicted the distribution of radiation emitted by a blackbody across different wavelengths. Despite its success, Planck's quantization theory was not immediately accepted by the broader scientific community. The idea that energy could be quantized was deeply counter to the prevailing view of classical physics, which had always treated energy as a continuous and measurable quantity. The concept of discrete energy levels seemed strange, and many scientists were reluctant to embrace such a radical departure from classical ideas. However, Planck's mathematical model was accurate, and over time, its implications became clearer. In the years following Planck's discovery, other scientists began to build on his work, most notably Albert Einstein. Einstein's explanation of the photoelectric effect in 1905 provided further evidence for the quantization of energy. In this work, Einstein proposed that light, traditionally thought to behave purely as a wave, could also be thought of as being composed of discrete particles, or photons. This idea was directly influenced by Planck's notion of energy quanta and further cemented the concept of quantization in the foundation of quantum theory. Einstein's work demonstrated that light could be understood in terms of discrete packets of energy, much like the way Planck had described the radiation emitted by blackbodies. This idea of duality, that light could exhibit both wave-like and particle-like behavior, was one of the cornerstones of quantum mechanics, and it was a direct consequence of Planck's insights. Einstein's contribution, alongside Planck's, showed that energy itself was not a smooth, continuous substance, but rather a collection of discrete, measurable units. This was a fundamental shift in how scientists understood the very nature of the universe. Planck's work did not stop with blackbody radiation. His theories formed the groundwork for the development of quantum mechanics, a theory that would eventually lead to a deeper understanding of atomic and subatomic systems. As quantum mechanics began to evolve, it became clear that the quantization of energy was not an isolated phenomenon, but part of a larger framework in which particles and waves could coexist in ways that classical physics could never have predicted. Planck's constant, He, played a crucial role in many of these later developments, acting as the bridge between classical and quantum physics. In the decades following Planck's discovery, the field of quantum mechanics grew exponentially. The contributions of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger helped to refine and expand upon Planck's original ideas. Bohr, for example, used Planck's concept of quantization to develop his model of the atom, which explained the discrete energy levels of electrons in atoms. Heisenberg's uncertainty principle and Schrödinger's wave equation further deepened the understanding of the quantum world and demonstrated the inherent unpredictability and non-deterministic nature of subatomic particles. While Planck's theory was initially met with resistance, it eventually became clear that his insights were not just correct, but fundamental to the structure of modern physics. Quantum mechanics emerged as one of the most successful and far-reaching theories in science, providing accurate predictions and explanations for phenomena that classical physics could not. It revolutionized fields ranging from atomic physics to chemistry, material science, and even cosmology. Planck's contribution was the spark that ignited this revolution. The technological implications of Planck's work cannot be overstated. Quantum mechanics has led to the development of technologies that have transformed the modern world. Semiconductors, lasers, and the computers we use today all owe their existence to the principles of quantum theory. Even in more futuristic fields like quantum computing and quantum cryptography, Planck's ideas continue to play a critical role. His discovery of energy quantization is at the heart of many of the technologies that define our digital age. Planck's legacy extends beyond just the technological advances that followed. His work also had a profound impact on the philosophy of science. The realization that the universe operates on principles that are fundamentally different from what we had previously imagined challenged not only our understanding of the physical world but also our philosophical notions about determinism, causality, and the nature of reality itself. The probabilistic nature of quantum mechanics, where outcomes can only be predicted in terms of probabilities, has raised important questions about the limits of human knowledge and the role of the observer in the process of measurement. Furthermore, Planck's revolution in physics paved the way for a more unified view of the physical universe. The ideas of quantum mechanics, together with Einstein's theory of relativity, have led to a more comprehensive understanding of the cosmos. Today, physicists continue to explore the potential for a unified theory that can explain both the very large, the cosmos, and the very small subatomic particles, a goal that was once thought to be impossible. In conclusion, Max Planck's discovery of energy quantization was one of the most significant turning points in the history of science. It marked the birth of quantum theory and laid the foundation for the scientific revolution that followed. His work not only solved a critical problem in physics but also opened the door to a new way of thinking about the universe. The legacy of Planck's revolution extends far beyond the confines of physics, influencing technology, philosophy, and even our broader understanding of the world around us. His discovery will continue to shape the future of science and technology for generations to come. Planck's contributions remain a testament to the power of insight, the courage to challenge established ideas, and the relentless pursuit of knowledge. Max Planck's introduction of the concept of energy quanta fundamentally altered our understanding of the universe. One of the pivotal aspects of his theory was the relationship between energy and frequency, captured by Planck's constant. This was not merely a mathematical construct, but the key to understanding the smallest actions in nature and, by extension, the foundations of quantum mechanics itself. The concept of energy quantization would serve as the cornerstone of all subsequent developments in quantum theory and provided a path forward for the discovery of new phenomena, including those explored by Albert Einstein, Niels Bohr, and others. The idea of energy quanta, proposed by Planck in 1900, was radical. Classical physics, in particular, Newtonian mechanics and thermodynamics, had established the idea that energy was a continuous quantity. The very notion of discontinuous energy was inconceivable to most scientists at the time. But Planck, while attempting to solve the problem of blackbody radiation, showed that energy could be absorbed or emitted only in specific, discrete amounts quanta. This was the birth of what would later become quantum mechanics, a theory that would transform our entire understanding of physics. At the heart of Planck's discovery was his formulation of the equation that described the energy of these quanta. The equation related the energy of a quantum to its frequency through the constant h, which Planck derived from the mathematical model he used to explain the radiation emitted by blackbodies. According to Planck's theory, energy A could only exist in discrete amounts given by the formula E equals h c.f, where f is the frequency of radiation. This relationship established that the energy of radiation was directly proportional to its frequency, with Planck's constant acting as the proportionality constant. Planck's constant was a revelation, a numerical value that remained constant across all instances where energy and frequency interacted. This constant, which has the value of approximately 6.626 times 10 negative 34 joule seconds, would become a fundamental quantity in quantum mechanics, the foundation of the entire field of quantum theory. While at first glance, this may seem like a small and insignificant number, in reality, it has had profound consequences for our understanding of nature at the most fundamental levels. It showed that there were limits to how precisely energy could be defined or measured, and the implications of this discovery would ripple throughout physics, leading to the development of a new theory of the atomic and subatomic world. The significance of this insight cannot be overstated. Planck's proposal that energy is quantized was the first step toward the realization that the universe operates on principles that are fundamentally different from the smooth, continuous world of classical mechanics. By introducing a constant that governed the interaction between energy and frequency, Planck laid the groundwork for understanding phenomena that classical physics simply could not explain. For example, one of the most famous experiments that showcased the validity of Planck's theory was the photoelectric effect, later explained by Albert Einstein in 1905. In this experiment, light shining on a metal surface caused the ejection of electrons, but only light of a certain frequency could produce this effect. This behavior could not be explained by classical wave theory, but Planck's concept of quantized energy could account for it. Einstein built on Planck's work to show that light itself is quantized and behaves both as a wave and as a particle, a concept that would go on to revolutionize our understanding of light and matter. As Planck's work began to be recognized and accepted, it was clear that the concept of quantization was not just a theoretical curiosity, but a fundamental property of nature. It suggested that on the atomic and subatomic scales, the classical view of continuous energy no longer applied. Instead, energy and matter could only exist in discrete amounts, a revelation that would pave the way for the development of quantum mechanics. The principle of energy quantization challenged the deterministic view of the universe, which had dominated science since Newton's time, and introduced the idea that at the smallest scales, the behavior of particles was inherently probabilistic. The quantum world, as it became known, was governed by principles that were completely alien to the classical worldview. For much of the early 20th century, this idea of quantization remained a topic of debate among scientists. Many, particularly those who were still rooted in the classical view of the world, found the idea of energy quanta difficult to accept. It wasn't until the work of scientists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who expanded upon Planck's ideas, that quantum mechanics began to take shape as a fully developed theory. Bohr's model of the atom, for example, relied heavily on Planck's quantization of energy. By incorporating Planck's constant into his atomic model, Bohr was able to explain the discrete energy levels of electrons in atoms, a mystery that had confounded scientists for centuries. In a similar vein, Schrödinger's wave equation, which describes the behavior of particles in quantum mechanics, was also based on the quantization of energy. This wave function, which Schrödinger introduced in 1926, described the probability distribution of particles and showed that particles could no longer be thought of as simple points in space. Instead, they existed as waves of probability, their positions and velocities only knowable in terms of probabilities. This departure from the classical notion of determinism further highlighted the revolutionary nature of Planck's insights. Planck's ideas also led to one of the most profound philosophical shifts in the history of science. The concept of quantization introduced a fundamental uncertainty into the fabric of reality. In the classical worldview, the universe was governed by predictable laws. If one knew the present state of a system, one could, in principle, predict its future behavior with certainty. But in the quantum world, uncertainty was intrinsic to the very nature of reality. This uncertainty principle, formulated by Heisenberg in 1927, became one of the cornerstones of quantum mechanics. It states that the more precisely one measures the position of a particle, the less precisely one can know its momentum, and vice versa. This radical shift in our understanding of the nature of reality has had profound implications not just for physics but also for philosophy and the way we view the world. The practical consequences of Planck's discovery were just as profound. While his work began as an attempt to solve a specific problem in thermodynamics, it ultimately laid the groundwork for a vast range of technological advancements. The understanding of quantized energy has led to the development of technologies that are integral to our daily lives. One of the most significant examples is the development of semiconductors, which form the backbone of modern electronics. The understanding of quantum mechanics and energy quantization made possible the creation of the transistors and microchips that power computers, smartphones, and all other modern electronic devices. Additionally, lasers, which operate based on the principles of energy quantization, have had applications ranging from medical technology to telecommunications. The advent of quantum mechanics also paved the way for the development of quantum computing, a field that promises to revolutionize computing power by exploiting the unique properties of quantum states. While practical quantum computers are still in the early stages of development, the potential applications of quantum computing are vast. From solving complex problems in chemistry and materials science to enhancing cryptography and cybersecurity, quantum computing is expected to bring about an era of unprecedented technological advancements. Looking back at the historical significance of Planck's discovery, it is clear that his work marked the beginning of a new chapter in the story of science. He was the first to glimpse the fundamental nature of reality that underpins the quantum world, and his insights have had far-reaching consequences for physics, technology, and philosophy. Planck's revolution is still unfolding today, with scientists continuing to explore the mysteries of quantum mechanics and pushing the boundaries of what is possible in terms of technology. His work stands as a testament to the power of scientific inquiry, the courage to challenge established ideas, and the enduring impact that one breakthrough can have on our understanding of the universe. In conclusion, Planck's revolutionary discovery that energy is quantized fundamentally changed the course of physics and set the stage for the development of quantum mechanics. His work transformed our understanding of energy, matter, and the laws of nature at the most fundamental levels. Planck's constant, which played a crucial role in his theory, remains one of the most important numbers in all of physics. His insights into the quantization of energy continue to shape the way we think about the universe and have led to the development of technologies that are integral to modern life. Planck's contribution to science cannot be overstated, and his legacy continues to influence the fields of physics, technology, and philosophy. Max Planck's concept of energy quanta did not only serve as a theoretical breakthrough, but it also introduced an entirely new way of thinking about the physical world. The introduction of Planck's constant, h, which connects energy to frequency, formed the bedrock upon which quantum mechanics was constructed. Planck's revolutionary ideas reshaped our understanding of the universe, challenging classical physics and setting the stage for the quantum revolution that would follow. To grasp the full significance of this transformation, we must explore how Planck's work expanded the boundaries of knowledge, how it led to the quantum theory, and how it remains foundational to modern physics and technology. The initial challenge that Planck faced was related to blackbody radiation, a phenomenon where a body absorbs and emits electromagnetic radiation perfectly. Classical physics, based on the laws of thermodynamics and the wave theory of light, could not explain the observed spectrum of radiation emitted by a blackbody. Classical predictions, especially using the Rayleigh-Jeans law, suggested that as the temperature increased, the emitted radiation intensity would grow infinitely as the frequency increased, which led to what is now known as the ultraviolet catastrophe. This prediction did not match experimental observations, as no physical object could emit infinite amounts of energy. The classical view failed, and it became clear that something deeper was at play in the interaction between energy and matter. Planck's insight came when he proposed that the energy of electromagnetic radiation is not continuous, but instead is emitted or absorbed in discrete, quantized amounts. These units of energy, or quanta, were directly proportional to the frequency of the radiation, with Planck's constant h acting as the proportionality factor. The energy E of a quantum of radiation was given by the equation E equals hfc.f, where f is the frequency of the radiation. This was a stunning departure from classical physics, which had assumed that energy could be varied continuously in any amount. One of the most important aspects of Planck's discovery was that the value of Planck's constant did not change, no matter the system or material being considered. This which has a value of approximately 6.626 times 10 negative 34 joule seconds, became a cornerstone of quantum mechanics and one of the most recognized constants in all of physics. Planck's constant marked a fundamental shift in how scientists thought about the universe. The idea that energy is inherently quantized meant that there were limits to how precisely certain physical quantities, such as energy or momentum, could be measured or predicted. The universe, at its smallest scales, would no longer be seen as a smooth, continuous entity, but instead would be governed by discrete, probabilistic events. The consequences of this realization were profound. By proposing energy quantization, Planck not only solved the blackbody radiation problem, but also set the stage for a series of discoveries that would forever change our understanding of the physical world. His work provided the first hint that the universe, at its core, operates in ways that are entirely different from the familiar world of classical physics. The discrete nature of energy suggested that there were fundamental limits to how much we could know about the smallest building blocks of nature. This idea of quantization would be expanded upon by other physicists, such as Albert Einstein, Niels Bohr, and Werner Heisenberg, leading to the development of the quantum theory that we know today. Planck's insights influenced many other key developments in physics. Einstein's work on the photoelectric effect, for example, directly built upon Planck's quantization hypothesis. In 1905, Einstein proposed that light itself is quantized and consists of discrete packets of energy called photons. This was the beginning of the wave-particle duality of light, a concept that would become central to quantum mechanics. Einstein's work demonstrated that light, which had been understood as a continuous wave phenomenon, also had particle-like properties. This discovery was in direct alignment with Planck's idea of energy quanta and provided further evidence for the validity of Planck's theory. In addition to Einstein, the development of the Bohr model of the atom also relied on Planck's concept of quantized energy levels. Bohr used Planck's constant to explain why atoms emitted radiation at discrete frequencies, resulting in the famous atomic spectral lines. His model of the atom, which posited that electrons could only occupy certain discrete orbits around the nucleus, directly stemmed from the quantization of energy. This model revolutionized our understanding of atomic structure and marked the beginning of quantum mechanics in chemistry and atomic physics. As the quantum theory continued to evolve, the implications of Planck's work became even more profound. The idea that energy is quantized led to the realization that matter, at its most fundamental level, behaves in a fundamentally different way than classical objects. The classical view of physics, which emphasized deterministic laws that governed the motion of objects, was replaced by a probabilistic approach in which particles could exist in multiple states simultaneously with their behavior governed by wave functions. This was captured by Heisenberg's uncertainty principle, which arose directly from the idea that energy is quantized. The uncertainty principle, which states that one cannot simultaneously know both the position and momentum of a particle with absolute precision, is a direct consequence of the quantization of energy and reflects the inherent unpredictability of quantum systems. The philosophical implications of Planck's work were equally profound. The idea that the universe operates in a fundamentally discrete manner, governed by probabilistic events, challenged long-standing assumptions about the nature of reality. Classical physics had assumed that the world was deterministic. If we knew the state of a system, we could predict its future. But in the quantum world, the behavior of particles could only be predicted in terms of probabilities. This realization prompted deep philosophical debates about the nature of reality, causality, and the role of the observer. The shift from a deterministic to a probabilistic view of the universe was one of the most radical changes in scientific thought and fundamentally altered our perception of the physical world. In practical terms, Planck's discovery laid the foundation for a number of technologies that have revolutionized the modern world. Quantum mechanics, which was built on Planck's insights, has led to the development of semiconductors, lasers, and the technology behind computers, smartphones, and the Internet. Without the concept of quantized energy and the developments that followed, the digital age we live in today would not have been possible. Additionally, quantum mechanics has had significant implications in fields ranging from cryptography to medical imaging and materials science. Quantum mechanics, as a result of Planck's discovery, has become one of the most successful and predictive scientific theories ever formulated. The principles of quantum theory are applied daily in a wide range of industries, from the development of new materials to the functioning of lasers and the processing of information in modern computing systems. In fact, many of the most transformative technologies of the 20th and 21st centuries, such as the transistor, the laser, and quantum computing, are direct descendants of the ideas that Planck introduced in his work on blackbody radiation. The study of quantum systems continues to be a rapidly advancing field, with new technologies and discoveries emerging every day. Quantum computing, for instance, promises to revolutionize computing power by using quantum bits, or qubits, which can exist in multiple states simultaneously. This potential could lead to breakthroughs in fields such as artificial intelligence, cryptography, and drug discovery. Quantum cryptography is already being used to develop unbreakable encryption systems that are far more secure than traditional methods. Planck's work continues to shape the landscape of modern physics, not just in theoretical research, but also in the application of quantum principles to practical technologies. His theory of energy quantization set in motion a series of discoveries that have forever changed our understanding of the universe and have paved the way for new technologies that continue to transform the world. Planck's ideas were not only a fundamental turning point in the development of physics, but also a monumental shift in human thought, a shift that continues to resonate in scientific and technological advances today. The legacy of Max Planck's discovery is not confined to the realms of physics. His work has had a lasting impact on science, technology, and philosophy, influencing everything from the development of quantum computers to our very conception of reality. Planck's insights into the quantization of energy laid the groundwork for some of the most important discoveries in the history of science, and his contributions remain at the heart of modern scientific inquiry. His ideas continue to inspire and shape the way we approach problems in physics, engineering, and beyond, marking him as one of the greatest minds in the history of science. Max Planck's discovery that energy is quantized is regarded as one of the most important breakthroughs in the history of science. It marked the beginning of quantum theory and signaled a profound shift in the way we understand the fundamental nature of reality. For centuries, classical physics had dominated the scientific worldview, and the belief in a continuous, predictable universe prevailed. Planck's insight, however, shattered this classical view and introduced the idea that at the microscopic level, energy exists in discrete quantities. This simple yet revolutionary idea laid the foundation for modern physics, reshaping not only our understanding of the physical world, but also leading to the development of new technologies that continue to shape our daily lives. Before Planck's breakthrough, scientists believed that energy could be freely divided and that it could be absorbed or emitted in any quantity. This was consistent with classical theories of energy, such as those proposed by James Clerk Maxwell and Lord Rayleigh. According to these classical theories, the energy emitted by a hot object could vary smoothly across a continuous spectrum of wavelengths. This was the basis of what was known as the theory of blackbody radiation, the study of the electromagnetic radiation emitted by an idealized object that absorbs and re-emits all forms of radiation that fall upon it. At the time, the study of blackbody radiation had posed a significant problem for physicists. The classical laws of radiation predicted that as the temperature of an object increased, the emitted radiation would increase indefinitely at shorter wavelengths, particularly in the ultraviolet range. This led to what is famously known as the ultraviolet catastrophe, where the classical predictions of energy output contradicted experimental observations. Instead of infinite energy being emitted, experiments showed that the intensity of radiation actually peaked at a certain wavelength and then dropped off, particularly at higher frequencies. This discrepancy between theory and experiment was a major challenge for physicists. The classical laws were simply unable to explain the observed data, and scientists were faced with a crisis in the field of thermodynamics. It was in this context that Planck, working at the University of Berlin, set out to resolve the issue. Planck's goal was not to challenge the entire framework of classical physics, but rather to find a way to reconcile the observed radiation spectrum with theory. Planck proposed a radical new hypothesis that energy is not emitted or absorbed continuously, as had been assumed by classical physics, but rather in discrete, quantized amounts. His insight was a simple one. Energy could only be emitted or absorbed in specific chunks or packets, which he called quanta. This was an entirely new concept in physics, one that ran counter to centuries of established thought. The energy of these quanta, Planck suggested, would be proportional to the frequency of the radiation. The relationship between energy and frequency could be expressed by the equation E equals hc dot F, where E is the energy of the quantum, F is the frequency of the radiation, and h is Planck's constant. Planck's constant, He, became one of the most fundamental constants in physics, marking the birth of quantum theory. This seemingly simple equation, now known as Planck's law, was the key to resolving the blackbody radiation problem. It allowed Planck to derive a new mathematical formula that accurately described the observed intensity of radiation emitted by a blackbody. The beauty of this equation was that it eliminated the ultraviolet catastrophe predicted by classical theory and provided a precise fit to experimental data. Planck's hypothesis of quantized energy, therefore, did more than solve a specific scientific problem. It opened the door to an entirely new way of thinking about energy and the behavior of matter at microscopic scales. Planck's constant, He, though small, became a cornerstone of modern physics. Its significance extends far beyond blackbody radiation and energy quantization. It is the key to understanding the quantum mechanical behavior of particles, energy, and waves. In fact, Planck's constant plays a critical role in every quantum theory that followed, including the development of the Schrödinger equation, Heisenberg's uncertainty principle, and the creation of quantum electrodynamics. The idea that energy is quantized had profound implications for how we understand the nature of particles and waves in the quantum world. The legacy of Planck's discovery is still felt today, both in the field of theoretical physics and in the practical applications that have emerged from it. Planck's work laid the foundation for the development of quantum mechanics, a theory that governs the behavior of particles on the smallest scales. It is a theory that has been remarkably successful in explaining the properties of atoms, molecules, and subatomic particles, and it has provided the framework for much of modern science and technology. One of the most striking aspects of Planck's work was its ability to challenge the deterministic view of the universe that had been established by Newtonian mechanics. Classical physics was built on the belief that the universe was governed by laws that could predict the future behavior of physical systems with absolute certainty. If one knew the position and velocity of an object, one could, in principle, calculate its future motion with great precision. But the quantum world, as described by Planck, is inherently probabilistic. Energy, matter, and even light exist in discrete states, and the behavior of particles is governed by probabilities rather than certainties. This shift from determinism to probability was one of the most profound changes in the history of science. Planck's discovery suggested that at the smallest scales of reality, the laws of nature were not as predictable and smooth as classical physics had imagined. Instead, particles existed in a realm of uncertainty, where the exact state of a system could only be described in terms of probabilities. This was later formalized by Heisenberg's uncertainty principle, which states that one cannot simultaneously know both the position and momentum of a particle with absolute precision. The advent of quantum mechanics, with Planck's discovery at its core, led to a complete rethinking of the laws that govern the universe. It made it clear that the classical, deterministic view of nature was insufficient for understanding the subatomic world. Planck's quantization of energy was the first step in what would become the most successful theory in the history of physics, able to explain a wide variety of phenomena that were previously inexplicable, from the behavior of atoms to the interactions of light and matter. This quantum revolution was not limited to the realm of theory. The practical applications of quantum mechanics, inspired by Planck's discoveries, have had a profound impact on technology. The most immediate and widely recognized examples of quantum technologies include the development of semiconductors, lasers, and modern electronics. Planck's work was directly responsible for the invention of the transistor, which revolutionized the electronics industry and gave birth to the digital age. Without the understanding of energy quantization, there would be no modern computers, smartphones, or communication technologies. Another remarkable technological application of Planck's theory is the development of quantum computers, which rely on the principles of superposition and entanglement to perform calculations far beyond the capabilities of classical computers. Quantum computers exploit the behavior of particles on the smallest scales, where quantum effects dominate. Planck's constant, as the defining quantity of energy quantization, is an essential part of the physics that underlies these cutting-edge technologies. In fact, the potential of quantum computing to solve complex problems in fields like cryptography, drug discovery, and materials science is one of the most exciting developments in modern physics. The legacy of Planck's work is also deeply embedded in the fabric of modern physics. His theories provided the framework for the later work of other physicists, including Albert Einstein, Niels Bohr, and Werner Heisenberg, all of whom expanded upon Planck's ideas and helped to shape the development of quantum mechanics. Without Planck's insight into energy quantization, the work of these scientists and the resulting advances in atomic physics, quantum chemistry, and particle physics would not have been possible. In conclusion, Max Planck's discovery that energy is quantized marked the beginning of a new era in physics. His insight into the discrete nature of energy fundamentally changed the way scientists understood the behavior of particles and waves at microscopic scales. Planck's constant, a fundamental quantity in quantum mechanics, became a cornerstone of modern physics and laid the foundation for a wide range of scientific and technological advances. The revolution Planck set in motion has not only transformed the way we think about the universe, but has also brought about innovations that continue to shape our modern world. Planck's work remains one of the most influential contributions to the development of modern science, and its implications are still being explored today. Max Planck's groundbreaking introduction of the concept of energy quanta was not only revolutionary, but also created a foundation that altered the entire landscape of physics and science. The birth of quantum theory, fueled by Planck's work, drastically changed the way scientists viewed the physical universe. Energy quantization, the idea that energy is not continuous but rather exists in discrete packets, reshaped our understanding of the microscopic world and initiated a chain of discoveries that continue to influence nearly every aspect of modern physics, technology, and even philosophy. Planck's approach to the problem of blackbody radiation was born out of necessity. In the late 19th century, physicists were attempting to understand the spectrum of radiation emitted by an idealized object, the blackbody, which absorbs and emits radiation at all frequencies. The classical theory of the time, based on Maxwell's equations for electromagnetism and the Rayleigh-Jeans law for radiation, predicted that at higher frequencies, such as ultraviolet light, the emitted energy would increase without bound. This prediction was physically nonsensical, as it suggested that objects could emit infinite amounts of energy, something that contradicted experimental observations. This discrepancy, known as the ultraviolet catastrophe, represented a major crisis in classical physics. The solution to this crisis came from Planck, who was studying the problem of blackbody radiation in the context of thermodynamics. Rather than simply applying existing classical models, Planck ventured into new territory. He introduced the idea that the energy of oscillators inside the blackbody could only take on discrete values. He proposed that energy could only be emitted or absorbed in quantized amounts, or quanta, which were proportional to the frequency of radiation. This was a radical departure from the continuous nature of classical theories. Planck's equation, E equals h.c.f, where A is the energy, F is the frequency, and h is the constant now known as Planck's constant, provided a mathematical framework to describe the intensity of radiation emitted by a blackbody at various frequencies. What made Planck's theory so revolutionary was not only the mathematical accuracy of his predictions, but the concept of energy quantization itself. It was the first time that scientists had to grapple with the idea that energy does not flow smoothly and continuously, but in discrete packets. This insight was the beginning of a new way of thinking about energy and matter, one that departed fundamentally from the classical Newtonian worldview. Planck's theory suggested that the universe, at its most basic level, operates in a fundamentally different way than previously thought, with discrete quantities governing the interactions of particles. Planck's constant, h, became one of the most important numbers in all of physics. The value of A is approximately 6.626 times 10 negative 34 joule seconds, a number so small that it is almost imperceptible at the macroscopic scale. However, at the microscopic scale, the significance of h is immense. It is the key to understanding the smallest interactions in nature, from the behavior of atoms to the way light and matter interact at the quantum level. Without Planck's constant, there would be no quantum mechanics, no understanding of atomic structures, and no modern technologies that rely on the principles of quantum physics. The shift from a continuous to a discrete understanding of energy had far-reaching consequences. It marked the beginning of the quantum revolution and forced scientists to rethink their approach to the laws of nature. Classical physics, which had been so successful in explaining macroscopic phenomena like the motion of planets, was no longer sufficient to explain the behavior of matter and energy at the atomic and subatomic scales. Instead, scientists would have to develop a new framework, quantum mechanics, that could account for the strange, counterintuitive behavior of particles that exhibited both wave-like and particle-like characteristics. One of the key aspects of Planck's discovery was its influence on the development of quantum mechanics. Planck's idea of quantized energy laid the groundwork for the work of other pioneers in the field, including Albert Einstein, Niels Bohr, and Werner Heisenberg. Einstein, building on Planck's concept of quantization, used it to explain the photoelectric effect, showing that light itself is quantized and composed of particles, or photons. This was a crucial step in the development of the theory of light as both a wave and a particle, a duality that would become a cornerstone of quantum mechanics. Bohr, in his model of the atom, applied the concept of quantized energy to explain the discrete energy levels of electrons in atoms. Bohr's model, which used Planck's quantization of energy to explain the spectral lines of hydrogen, was one of the first successful applications of quantum ideas to atomic physics. The concept of quantized energy levels was revolutionary, as it explained why atoms could only absorb or emit certain wavelengths of light. This was a significant departure from classical ideas, which could not explain why atoms emitted light only at specific frequencies. Planck's quantization also led to the development of Heisenberg's uncertainty principle. Heisenberg's principle, which states that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision, was a direct consequence of Planck's work. The uncertainty principle revealed the inherent limits of measurement at the quantum level, highlighting the fundamental role of probability in the behavior of subatomic particles. The uncertainty principle, along with Planck's quantization, marked a major shift in our understanding of the physical world. The deterministic, predictable universe of classical physics was replaced by a probabilistic quantum world where events could only be predicted in terms of likelihoods rather than certainties. This probabilistic nature of quantum mechanics, which was born from Planck's discovery of quantized energy, has profound philosophical implications. For centuries, the classical view of the universe had been one of determinism. If one could know the position and velocity of a particle, one could predict its future behavior with certainty. Planck's theory, however, and the subsequent development of quantum mechanics showed that the universe, at its most fundamental level, is not deterministic but probabilistic. This realization changed not only our scientific understanding of the universe, but also our philosophical outlook on the nature of reality. The quantum world, unlike the classical world, is not predictable with absolute certainty, and this has led to new ways of thinking about causality, free will, and the nature of existence itself. Beyond the theoretical implications, Planck's discovery also had practical consequences that continue to shape our modern world. The principles of quantum mechanics, built on Planck's quantization of energy, have led to the development of a wide range of technologies that are integral to our daily lives. One of the most significant contributions of quantum mechanics has been the development of semiconductors and transistors, which form the backbone of modern electronics. These technologies are the result of understanding how electrons behave in quantum systems and have paved the way for the creation of everything from computers and smartphones to medical imaging devices and lasers. Lasers, another technological marvel that arose from quantum theory, operate on the principles of energy quantization. A laser works by stimulating atoms to emit light at specific frequencies based on the discrete energy levels of electrons. The discovery of lasers, which relies on Planck's ideas of quantized energy, has led to advances in communication, entertainment, medicine, and manufacturing. Another revolutionary application of Planck's work is in the field of quantum computing. Quantum computers, which rely on quantum bits, or qubits, exploit the strange properties of quantum mechanics, such as superposition and entanglement, to perform calculations much faster than classical computers. Quantum computing holds the potential to solve problems that are currently beyond the capabilities of traditional computing, such as simulating complex chemical reactions, optimizing supply chains, and breaking encryption codes. The ongoing development of quantum technologies is a testament to the enduring relevance of Planck's ideas. What started as a theoretical breakthrough aimed at solving a specific problem in radiation theory has become the foundation for an entire field of science and technology that continues to evolve. From the development of lasers to the potential of quantum computers, Planck's insights into energy quantization have led to innovations that impact nearly every aspect of modern life. Max Planck's discovery that energy is quantized is not just an important chapter in the history of physics, it is a cornerstone of modern science. His work opened the door to a new way of thinking about the universe, one that embraces the probabilistic, discrete nature of energy and matter. The implications of his discovery continue to unfold, reshaping our understanding of the cosmos and driving technological advancements that are transforming the world. Planck's legacy is not just in the equations he wrote, but in the far-reaching consequences his work had on the development of physics, technology, and our understanding of reality itself. Max Planck's discovery of energy quantization was a pivotal moment in the history of physics, marking the birth of quantum theory. This revolutionary idea not only resolved the blackbody radiation problem, but also fundamentally changed the way scientists understood the behavior of energy and matter at microscopic scales. Planck's work laid the groundwork for the development of quantum mechanics and altered the course of modern science, leading to breakthroughs that continue to shape our understanding of the universe today. Planck's approach to the blackbody radiation problem involved a radical shift in thinking. Classical physics, which was grounded in the continuous nature of energy, could not explain the observed intensity of radiation emitted by a blackbody at various frequencies. Classical models predicted that at higher frequencies, energy would increase indefinitely, which led to what was known as the ultraviolet catastrophe. This prediction conflicted with experimental data, which showed that energy emitted by blackbodies reached a peak at a certain wavelength and then dropped off. Planck proposed that instead of being emitted continuously, energy was quantized, meaning it could only be absorbed or emitted in discrete packets, or quanta. This hypothesis resolved the ultraviolet catastrophe and explained the observed radiation spectrum, marking the first step toward the quantum revolution. The key innovation in Planck's theory was the introduction of the concept of Planck's constant, denoted by h. This constant, approximately 6.626 times 10 negative 34 joule seconds, became fundamental to the understanding of quantum mechanics. Planck's equation, E equals h/c dot f, where E is the energy of a quantum and f is the frequency of radiation, provided a mathematical relationship between energy and frequency. This equation showed that energy is directly proportional to frequency, but with a fixed constant, which was a departure from the classical view that energy could vary continuously. Planck's constant remains one of the most important constants in physics and is central to nearly all quantum phenomena. The impact of Planck's discovery extended beyond the resolution of the blackbody radiation problem. His work provided the foundation for the development of quantum mechanics, a theory that would explain the behavior of matter and energy at the atomic and subatomic levels. Albert Einstein, Niels Bohr, Werner Heisenberg, and others built on Planck's ideas to develop quantum mechanics, which revealed that particles do not follow predictable, continuous paths, but rather behave in probabilistic ways. This departure from classical determinism was a major philosophical shift, suggesting that the universe at the microscopic scale is governed by uncertainty and probability, rather than certainty and predictability. In addition to its theoretical significance, Planck's discovery had profound practical implications. Quantum mechanics, born out of Planck's quantization of energy, has led to the development of technologies that have transformed the modern world. Semiconductors, lasers, and computers are all products of quantum theory. For instance, transistors, which are the building blocks of modern electronic devices, rely on the principles of quantum mechanics to control the flow of electricity. Lasers, which are used in a wide range of applications from medicine to telecommunications, operate based on the principles of energy quantization. These technologies, along with others based on quantum principles, have revolutionized industries and everyday life, making Planck's work one of the most influential contributions to science and technology in the 20th century. Planck's discovery also sparked a broader philosophical shift. The quantization of energy challenged the classical view that the universe operates in a continuous, deterministic manner. Instead, the quantum view introduced the idea that, at the most fundamental levels of reality, uncertainty and probability are intrinsic properties. This shift in understanding not only affected physics but also had deep implications for our conception of the nature of reality, causality, and the limits of human knowledge. The probabilistic nature of quantum mechanics, highlighted by Heisenberg's uncertainty principle, suggested that the universe is inherently unpredictable and that even with perfect knowledge of a system's state, we could never predict its future behavior with complete certainty. The legacy of Max Planck's work extends far beyond the immediate implications of quantum mechanics. His ideas continue to influence scientific research, technology, and philosophy today. Planck's constant remains central to the equations that describe the quantum world, and his approach to quantization laid the foundation for future developments in fields such as quantum computing and quantum cryptography. The revolutionary ideas that Planck introduced, from the quantization of energy to the development of probabilistic models of the universe, have shaped the way we understand the cosmos and continue to drive innovation in both theoretical and applied sciences. In conclusion, Max Planck's discovery of energy quantization was a turning point in the history of science. His introduction of Planck's constant and the concept of quantized energy resolved a major issue in classical physics and opened the door to the development of quantum mechanics. This discovery reshaped the way scientists understand the universe, leading to a new framework for describing the behavior of particles and energy at the atomic and subatomic levels. It also led to the development of technologies that have had a profound impact on modern society. Planck's work remains foundational to modern physics and continues to inspire new discoveries and technological innovations that shape the future of science and technology. Max Planck's discovery that energy is quantized is widely regarded as one of the most profound contributions to the field of physics. This fundamental insight not only resolved a long-standing problem in blackbody radiation, but also laid the foundation for the development of quantum mechanics. Planck's revolutionary hypothesis that energy is emitted or absorbed in discrete packets, or quanta, fundamentally changed the way we perceive the behavior of energy and matter on a microscopic scale. This theory not only solved the issues of the time, but also triggered an entirely new era of scientific thought, offering a deeper understanding of the physical world. The context of Planck's work begins with the challenge posed by the classical understanding of radiation. Classical physics, based on Newtonian mechanics and Maxwell's electromagnetic theory, had provided a solid framework for understanding many physical phenomena. However, when it came to explaining the spectrum of radiation emitted by a blackbody, classical theories failed. According to classical physics, as the temperature of an object increased, the intensity of the radiation would grow infinitely at shorter wavelengths, leading to what was known as the ultraviolet catastrophe. This paradox in classical physics prompted the need for a new theory that could reconcile the observed data with the predictions made by the classical models. Planck's breakthrough came when he proposed that energy could not be emitted continuously, as classical theory suggested, but only in discrete units. This was a radical departure from the traditional view. He hypothesized that the energy of a system is proportional to the frequency of radiation, with the proportionality constant being a fundamental number, now known as Planck's constant. This allowed him to develop a mathematical model that accurately described the observed radiation from a blackbody. Planck's equation, E equals hc dot F, where E is the energy, F is the frequency of the radiation, and h is Planck's constant, was the key to solving the blackbody radiation problem. His work thus bridged the gap between classical physics and the emerging quantum theory. Planck's constant, denoted by h, is a value that has become one of the most important constants in physics. It is approximately 6.626 times 10⁻34 joule seconds, and serves as the fundamental scale for quantizing energy. The introduction of this constant revealed that the classical view of energy as a continuous variable could not explain the behavior of matter at microscopic scales. Instead, energy must be treated as discrete and quantized, fundamentally altering how scientists approach the study of matter and energy. This was the first glimpse into the quantum world, a world where the classical laws of physics no longer applied and where uncertainty and probability took center stage. The revolutionary nature of Planck's discovery became more apparent as other scientists, most notably Albert Einstein, began to build upon his ideas. Einstein's explanation of the photoelectric effect, for instance, was a direct consequence of Planck's theory. Einstein proposed that light itself behaves as both a wave and a particle, with the energy of each light particle, photon, being quantized according to Planck's relation. This duality of light, where it exhibits properties of both waves and particles, became one of the foundational ideas of quantum mechanics. Einstein's work demonstrated that Planck's ideas about energy quantization applied not only to thermal radiation, but also to the interaction of light and matter, thus extending Planck's revolutionary insight into new realms of physics. The implications of Planck's work were profound, and they set the stage for the development of quantum mechanics, which would reshape the entire landscape of physics. Quantum mechanics, a theory that deals with the behavior of particles on the atomic and subatomic scales, emerged in the early 20th century, building on Planck's quantization of energy. This new theory offered a probabilistic approach to understanding the behavior of particles, a stark contrast to the deterministic nature of classical mechanics. Niels Bohr's model of the atom, which used Planck's quantization to explain the discrete energy levels of electrons, and Werner Heisenberg's uncertainty principle, which stated that the position and momentum of a particle cannot both be precisely measured simultaneously, were among the many advancements that emerged from Planck's original insight. The significance of Planck's discovery goes beyond its immediate effects on theoretical physics. The quantum theory that Planck helped to establish has had a profound impact on technology. Modern electronics, the development of semiconductors, lasers, and even the computers we use today owe their existence to the principles of quantum mechanics, which were built upon Planck's quantization of energy. Quantum mechanics has also given rise to cutting-edge technologies like quantum cryptography, which promises to revolutionize secure communication systems. In addition, the emerging field of quantum computing, which aims to harness the power of quantum states to perform computations that classical computers cannot, is a direct descendant of Planck's work. This makes Planck's contribution not just a theoretical advance, but a practical one that continues to drive technological progress in the 21st century. Max Planck's work also brought about a philosophical shift. The idea that energy is quantized and that the universe operates on probabilistic laws rather than deterministic ones raised important questions about the nature of reality. Planck's theory revealed that, at the quantum level, the behavior of particles cannot be precisely determined. Instead, it can only be predicted in terms of probabilities. This concept of uncertainty, later formalized by Heisenberg, radically altered our understanding of nature. It also blurred the lines between science and philosophy, prompting discussions about the limits of human knowledge and the role of the observer in shaping the reality we experience. In conclusion, Max Planck's discovery of energy quantization was a turning point in the history of physics. It resolved a critical problem in classical thermodynamics and provided the foundation for quantum mechanics, a theory that has since transformed our understanding of the universe. Planck's constant became a fundamental quantity in modern physics, and his insights laid the groundwork for the development of technologies that have revolutionized the modern world. His work also introduced new philosophical questions, challenging long-held beliefs about determinism and the nature of reality. Planck's legacy continues to influence both scientific theory and practical technology, making him one of the most important figures in the history of science. Max Planck's discovery of energy quantization is one of the most transformative breakthroughs in the history of physics. His insight into the discrete nature of energy opened the door to quantum mechanics and reshaped our understanding of the microscopic world. Prior to Planck, classical physics, which had successfully explained a wide range of phenomena, was unable to account for certain behaviors, especially in the realm of blackbody radiation. Planck's work provided a solution to this problem, and in doing so, changed the course of scientific inquiry forever. Planck's work began with the problem of blackbody radiation, which was a long-standing challenge in thermodynamics. A blackbody, by definition, absorbs all radiation that falls on it and emits radiation at various wavelengths. Classical physics predicted that as the temperature of a blackbody increased, the amount of radiation it emitted would increase indefinitely at shorter wavelengths. This led to the ultraviolet catastrophe, a prediction that defied experimental results. Experimental data showed that the radiation emitted by blackbodies did not increase infinitely at short wavelengths, but instead followed a peak pattern before tapering off. This discrepancy between theory and observation was a critical issue that needed resolution. To solve this, Planck proposed that energy was not emitted or absorbed continuously, but in discrete units or quanta. This hypothesis was revolutionary because it contradicted the classical view, which saw energy as a continuous variable. Instead, Planck suggested that the energy of a quantum was proportional to the frequency of radiation. This led to the famous equation E equals h c dot f, where E is the energy of the quantum, Fa is the frequency of the radiation, and He is Planck's constant. This was the first instance in which energy was shown to be quantized, and it provided an explanation for the observed blackbody radiation spectrum. Planck's constant, denoted by h, became one of the most significant constants in all of physics. Its value, 6.626 times 10, negative 34, joule seconds, is small, yet it plays a fundamental role in the equations of quantum mechanics. The introduction of Planck's constant had deep implications. It suggested that on the atomic and subatomic scales, the classical notion of continuous energy was no longer valid. Instead, energy is discrete and comes in specific quantities determined by the frequency of the radiation. This was a profound shift in the scientific worldview, indicating that at the smallest scales, the universe operates under entirely different principles than those governing the macroscopic world. While Planck's work was initially met with skepticism, it laid the foundation for the quantum revolution. It directly influenced the development of quantum mechanics by providing the first theoretical framework that could explain phenomena such as the behavior of electrons in atoms, the emission spectra of elements, and the dual nature of light. The quantization of energy would later be expanded upon by Albert Einstein, who applied Planck's idea to explain the photoelectric effect, and by Niels Bohr, who used it to explain the stability of atomic orbits. Without Planck's insight, these groundbreaking developments in quantum theory would not have been possible. The probabilistic nature of quantum mechanics, which was revealed through Planck's work, marked a philosophical shift in the understanding of the universe. Classical physics was built on the assumption of determinism, the idea that, if the current state of a system is known, its future behavior can be predicted with certainty. However, quantum mechanics, which arose from Planck's quantization of energy, introduced uncertainty and probability into the equation. This shift was epitomized by Heisenberg's uncertainty principle, which stated that certain pairs of physical properties, such as position and momentum, could not both be precisely known at the same time. The probabilistic nature of quantum mechanics challenged the classical deterministic worldview and opened up new questions about the nature of reality itself. The implications of Planck's work reached far beyond the theoretical realm. The principles of quantum mechanics, based on the idea of energy quantization, have led to numerous technological advancements. For example, semiconductors and transistors, which are the building blocks of modern electronics, rely on quantum mechanics to function. These devices form the foundation of virtually all modern electronic technologies, from computers and smartphones to medical equipment and communication systems. Additionally, lasers, which operate on the principles of quantum mechanics, have had wide-ranging applications in medicine, communications, manufacturing, and entertainment. The development of quantum technologies, such as quantum computing and quantum cryptography, is a direct extension of Planck's original discovery. Planck's discovery not only revolutionized physics but also had far-reaching impacts on technology, philosophy, and our understanding of the universe. It marked the beginning of the quantum age, which has given rise to powerful new tools for understanding and manipulating the natural world. Quantum mechanics, with Planck's energy quantization at its core, continues to drive scientific and technological progress. The legacy of Planck's work is not only in the equations he derived or the theories he proposed, but also in the profound influence his ideas continue to have on the development of modern science and technology. In conclusion, Max Planck's discovery of energy quantization was a transformative event in the history of science. By showing that energy is discrete rather than continuous, Planck opened the door to quantum mechanics, a theory that has since revolutionized our understanding of the universe. His work laid the groundwork for the development of modern physics, which has reshaped technology, philosophy, and science in ways that were unimaginable before. Planck's constant remains a fundamental element in quantum theory, and his discovery continues to have lasting effects, influencing both scientific research and the practical technologies that shape our daily lives. Max Planck's discovery that energy is quantized is one of the most pivotal events in the history of modern science. This breakthrough laid the foundation for the field of quantum mechanics, which fundamentally transformed our understanding of the universe, particularly at microscopic scales. Before Planck, classical physics had dominated scientific thought, and the belief in a continuous, predictable universe prevailed. Planck's insights challenged these established ideas and revealed that energy, rather than being a continuous variable, exists in discrete packets, a concept that would forever change the course of scientific inquiry. The problem that led Planck to his discovery was related to the phenomenon of blackbody radiation. A blackbody is an idealized object that absorbs and emits all types of radiation. Classical physics, particularly the laws derived from Maxwell's equations, predicted that the radiation emitted by such a body would increase infinitely as the temperature increased, especially at higher frequencies. However, experimental data showed that this was not the case. Instead, the intensity of radiation peaked at a certain wavelength and then decreased. This discrepancy between theory and observation, known as the ultraviolet catastrophe, was a critical problem that needed resolution. Planck's approach to solving this problem was radical. Instead of adhering to the classical understanding of energy as a continuous quantity, he proposed that energy could only be emitted or absorbed in discrete amounts, which he called quanta. He suggested that the energy of each quantum was proportional to the frequency of the radiation, leading to the formula E equals hc.f, where E is the energy of a quantum, F is the frequency, and esh is a constant, now known as Planck's constant. This equation not only solved the problem of blackbody radiation, but also introduced the concept that energy is quantized, a foundational principle of quantum mechanics. Planck's constant, denoted by h, became one of the most significant numbers in all of physics. Its value, approximately 6.626 times 10 negative 34 joule seconds, is incredibly small but incredibly important for understanding the behavior of energy and particles at the microscopic level. This constant encapsulates the idea that the smallest possible amount of energy is determined by the frequency of radiation, marking a departure from the continuous energy concepts that dominated classical physics. The introduction of Planck's constant brought a new way of looking at the world at the atomic scale, where classical physics no longer applied. The implications of Planck's work extended beyond the immediate problem of blackbody radiation. His ideas laid the groundwork for the development of quantum mechanics. Scientists such as Albert Einstein, Niels Bohr, and Werner Heisenberg would later build upon Planck's discovery to formulate the broader quantum theory. Einstein's explanation of the photoelectric effect, which showed that light could be thought of as quantized packets of energy, built directly on Planck's notion of quantization. Bohr's model of the atom, which proposed that electrons orbit the nucleus in discrete energy levels, also relied on the quantization of energy. These developments would lead to the emergence of quantum mechanics as a fully realized theory. In addition to its theoretical significance, Planck's work had profound practical implications. The understanding of quantized energy became the cornerstone of many technologies that define the modern world. Semiconductors, which are the building blocks of modern electronics, rely on the principles of quantum mechanics. The invention of the transistor, which enabled the development of computers and other electronic devices, would not have been possible without Planck's insights. Lasers, which are used in everything from telecommunications to medical procedures, also operate based on the principles of energy quantization. The modern world, with its array of electronic devices and technologies, owes much of its existence to the ideas Planck introduced. Beyond its impact on technology, Planck's discovery reshaped our philosophical understanding of the universe. Classical physics had presented a deterministic view of nature, where the behavior of systems could be predicted with certainty. However, Planck's quantization of energy suggested that at the atomic and subatomic levels, the universe operates probabilistically. This shift from a deterministic to a probabilistic worldview was one of the most profound changes in scientific thought. It led to the development of Heisenberg's uncertainty principle, which states that one cannot simultaneously know both the position and momentum of a particle with complete certainty. This idea of inherent uncertainty challenged the classical view of a predictable, deterministic universe and introduced a new way of thinking about the nature of reality. The philosophical and technological ramifications of Planck's discovery continue to reverberate in modern science. The principles of quantum mechanics, which Planck helped to establish, are used to understand and manipulate the most fundamental aspects of nature. Quantum technologies, including quantum computing, quantum cryptography, and quantum sensors, are poised to revolutionize fields such as computing, communication, and security. These emerging technologies, which rely on the behavior of particles at the quantum level, hold the potential to solve problems that classical computers and systems cannot. Quantum computing, in particular, promises to revolutionize areas such as artificial intelligence, optimization, and drug discovery by providing computational power far beyond that of current systems. In conclusion, Max Planck's discovery of energy quantization marked the beginning of a new era in physics. His insight into the discrete nature of energy, encapsulated by Planck's constant, fundamentally altered the way scientists understood the behavior of matter and energy. Planck's work not only solved a long-standing problem in blackbody radiation, but also paved the way for the development of quantum mechanics, a theory that has had profound implications for both theoretical physics and practical technology. The impact of Planck's discovery extends far beyond the laboratory, influencing the technologies that define the modern world and shaping our understanding of the universe at its most fundamental level. Planck's work remains a cornerstone of modern physics and continues to inspire new discoveries in science and technology today.